Based on everything we've seen in the chapter so far, we are now ready to get into quantum mechanics. First, we're going to start with the Heisenberg uncertainty principle. The pieces were now all in place for a way to rationalize all these seemingly contradictory wave and particle behaviors of both light and matter. But first, another weird observation. A driving force behind physics has been the criticality of making accurate measurements of physical phenomena and making predictions based on those measurements. This still holds true for quantum physics, but with a twist. There are times when the more accurate a measurement that you make of one quantity, the less accurate measurement you can make of a complementary quantity. This makes no sense to us at our macro level. However, in quantum physics, this is what happens. And this is expressed in the Heisenberg uncertainty principle, published by Walter Heisenberg in 1927. The first two quantities that will be discussed here that cannot both be measured precisely at the same time are momentum and position. The more accurately that you can observe the momentum, the less sure you are of where the particle, whether it's a photon, electron, or neutron, etc., is located. This imprecision or uncertainty is represented by delta px for momentum, and now we're talking about the x direction. That really could be either for the y or z, doesn't really matter here, and delta x for the position in the x direction. Here's the equation. This is the Heisenberg uncertainty principle. It tells you that the uncertainty in the measurement of the momentum times the uncertainty of the position measurement has to be greater or equal to Planck's constant. Now remember earlier when Max Planck came up with this, he actually wanted it to disappear, and here it turns up in the Heisenberg uncertainty principle, again as a fundamental property of the universe. This equation actually does work at the macro level, the level that we all can see. For example, if we take a car, the uncertainty in its momentum times the uncertainty in its position has to be greater than or equal to h, Planck's constant. If that's the case, why do we feel we can very accurately measure everything we need to know about a car's size and its momentum at the same time? Because Planck's constant is so very small. Recall that h is 6.63 times 10 to the minus 34th joule seconds. So when we use the uncertainty principle and we can measure the car, let's say we can measure where it is exactly to 1 millimeter or 10 to the minus 3 meters. We can then find its momentum to a precision of, we have delta p times delta x is greater than or equal to h. We divide both sides by delta x. We substitute the numbers, and then we find that the uncertainty in our measurement of the momentum has to be greater than 6.63 times 10 to the minus 28 Newton seconds. We certainly don't have any instruments that can measure a car's momentum that precisely, so we don't feel any restriction at all from the uncertainty principle. The uncertainty principle also helps explain why electrons remain in their orbits and do not collapse down into the nucleus. Niels Bohr had theorized that if an electron is in a quantized orbit, it does not radiate electromagnetic waves, so it does not lose energy, so it won't spin down into the nucleus. De Broglie showed that if the circumference of the orbit is equal to an integral number of the de Broglie wavelength, it also will just stay in that orbit and not collapse into the nucleus. Now if we look at Heisenberg's principle, let's try and move the electron very close to the nucleus. And we're going to call the distance delta r instead of x, y, or z, r meaning radius. So the radius gets very small. Now if the radius, here the delta x or the delta r, gets very small, the momentum has to increase. So it will get very, very large, the uncertainty in the momentum. So that tells you that this larger momentum won't enable the electron to stay inside the atom. So it just can't happen. You can't get the electron so close to the nucleus without getting a very, very large momentum which will actually move it away. So this is another reason why atoms stay together and the electrons don't collapse into the nucleus. There's another version of the uncertainty principle that relates energy and time as shown right here. The uncertainty in the measured energy of a particle times the uncertainty in the time has to be greater than or equal to Planck's constant. Fortunately, for everybody making measurements at levels that we can see, the Heisenberg uncertainty principle does not affect them due to the very small value of Planck's constant.